if we're going to truly count or truly find the magnetic field for a current loop, we probably can only do it for some places that offer us a certain amount of symmetry, at least with the mathematical skills that we have. And although I say it can probably be done for here, I don't want to do it. I'm not sure I can. I think I've forgotten how to. I'd have to do more work than I want to. So how about we just shoot for a problem in which we can find the magnetic field at just the middle of the loop? Does that make sense? That gives us a certain amount of symmetry. So, and this is the pretty typical question you should be able to do, which is finding the magnetic field in the middle of a loop of current using the Biot Savart law, which I was told I spelled wrong. I got the Biot part right, and I'm probably saying it wrong. It's French, is that right? And it's S-A-V-A-R-T, no E at the end. Is that right? Any French speakers? Vicky? No? No, you don't know how to say it, or no, you're not a French speaker?
Oh, I'm not a French speaker.
Oh, okay. I don't know anybody else want to offer to go? Yeah? No, how do you say it? That's it? I was okay? Biot Savart? You don't say the T? So Biot Savart?
Yeah.
All right. Yeah? Oui, oui. All right. So I'm going to erase all this stuff, and we're going to focus on finding the magnetic field at the very center of the current loop. And again, a reminder to all of you in class, we are leaving out this part of the wire, okay? We're only talking about the loop of current. We'll talk about the long straight wire in a minute, and then we'll be able to add the two together to get the total magnetic field. Does that make sense? So we're doing just the loop portion of the current. Like any of these problems in which we have a sum, we're going to need to set up the sum here to do this correctly. So let's start by looking at the tenets of what the sum is about. So we'll start with the easy part. We want to add up for the entire loop mu naught over 4 pi. That one's easy. That's a constant. That's going to come out of my integration. I is the current in the loop. That is also a constant. It's going to come out of the integration. We're assuming a constant current is passing through the wire. It's the next part that I have to worry about. ds cross r. All right, so let's pick a ds. ds represents a length of wire. Since this is a current loop, its direction is going to be tangent to the loop. So we can choose our direction for our ds as being tangent to the loop. Now, r is a unit vector that points from our loop to the point that we are looking for the magnetic field. So if we're looking for the magnetic field in the center here, r hat is going to be a vector that is, well, it looks to be radial. It'll have to be this way because it points to the center of the loop. So this will be the direction of r, This will be the direction of r hat, and this is the direction of ds. Now, I'm going to make the argument that although we have to do a cross product, which involves the sine of the angle between ds and r hat, can we all agree that for every single part of the loop, it's going to be the sine of 90 degrees? So we can just put that sine of 90 degrees here and leave our ds over r squared here. Now, the next part I think is going to be relatively straightforward, but let's see. R represents the distance from here to here, or in this case, from here to here. Can we also make the agreement that since r is the distance from the center of the loop to a point on the loop, that all the r's will be the same? Let's call that capital R, just to differentiate it from the placeholder of lowercase r, which means I can write this as r squared. All right? So we can talk about calculating ds two different ways. But since everything else is a constant, let's go ahead and collect all the constants and realize that I have ds as a small piece of length along the loop. And now I need to add up all of that length. Now look, it shouldn't be hard to realize that the length of this loop is going to be 2 pi r. Would you guys agree? It's a circumference. However, I want to remind you, I would like you to be able to do more complicated sums. So the other way to consider this is to say that ds is equal to r d theta. And we can pick a point, say here, to say this is going to be 0, where theta equals 0. So if this is our starting point, then we can say this is mu naught I over 4 pi r squared times r d theta, and we're going to sum that from 0 to 2 pi, and this should give us the entire magnetic field. I mean, yeah, we know it's got to work out to be 2 pi r, but if the current were not uniform, or if the shape were something different and we needed a more elaborate way to do it, I want to make sure you understand you can always go to that. Just make sure you pick a place that you're going to call 0, your point of reference, and then start your measurements from there. And still, this works out to be something that's pretty easy. Mu naught I over 4 pi r squared times 2 pi times r. And we can do a little simplification and get mu naught I over 2r. That's it. So this is the magnetic field in the center of a loop of current. So current loop, mu naught I over 2r. Not terrible? Pretty okay? Everybody good with that? All right. The next one's the hard one. So you ready to do the next one? Because the next one's got some stuff in it. So let's go ahead and do the next one. We need a long current carrying wire. Long current carrying wire. We're going to be located here. This is where we want to find out the magnetic field at point P. For consistency's sake, because we were talking about this distance being r and there being a long current carrying wire here, I'm going to call this perpendicular distance capital R. Is that okay with all of you guys? Just for consistency, so we can add it together with the other one in a minute. But R represents the perpendicular distance from point P to the wire. So again, we want to set up our situation. So I'm going to write out my function. A contribution to the magnetic field will equal mu naught over 4 pi times I ds cross r hat over r squared. Well, we'll assume a constant current passing in our wire. And if there's a constant current passing through our wire, we know that that makes I a constant. Mu naught and 4 pi will be constants. So we could start by just separating those things out. Mu naught I over 4 pi. Except now we do have an issue, right? At least a couple of them. If, let's say ds represents this piece of wire right here. This is a small piece of wire which we will call ds. It's, of course, got a vector component that is in this direction. That's the direction of ds. But r, unfortunately, r points this way. So this is our angle. Not ideal. So although I can write this as ds, and we'll just call this phi, sine of phi over r squared, it seems to me that for every ds, there will be a different angle and a different r squared. You guys all agree with that? Understand the problem that we have? We face a problem. One interesting thing, though, is the magnetic field is going to be out of the board for all points on this side of the wire and into the board for all points on this side of the wire. So every single component of ds is going to contribute to a magnetic field in the same direction, just by just using that thumb rule, right? The magnetic field curls out of the board on this side and into the board on this side. And it doesn't matter whether the ds is here or the ds is there. So all of the current is going to contribute to a magnetic field in the same direction. The electric field wasn't like that, if you remember. The electric field contributed to electric fields that were always in different directions. But at least this time, all of the magnetic fields contribute to a direction of the magnetic field that is going to be out of the page on the top. So that part we've got handled, the direction. But we still have to find a way to write this in terms of either phi or r. So we have a couple ways we could go about doing this, and we've talked about this before. I think the best way for us to do that would be to say, make this 0, and make this distance, say, s. And we can say that r is r squared plus s squared to the 1/2 power. That look good to you guys? And we could say that sine of phi, well, sine of phi is going to be r over r squared plus s squared to the 1/2 power. Is that what you guys get to? Or are you guys getting something else? I'm using this triangle and knowing that sine is positive in the first two quadrants. So whether I use this phi or I use this phi, I get the same answer. So that's why I think that'll work for our sine. We could do it different. We could do it all in terms of the angle, or we could do it all in terms of s. I'm putting it all in terms of s. Does that seem good for you guys? All right, so just throw it all in there now. All right, mu naught I over 4 pi times, okay. Sine phi is going to be r over r squared plus s squared to the 1/2 times 1 over r squared is going to be 1 over r squared plus s squared. And that'll all be times ds. That look good to you guys? And it don't look any fun to me, but you guys are now in second semester of calculus, suggesting that you could maybe do this one. I'm gonna give you some let's do some suggestions here. Can we all agree that this part of the wire will contribute the same amount to the magnetic field as this part of the wire? That there's a certain amount of symmetry there? So how about we go multiply by 2 and integrate from 0 to infinity? And that is going to be our magnetic field at point P. All right. This sounds like a job for you guys, because you're strong calculus students. Let's pull all the constants out. That should help. I'll have mu naught I 2 r over 4 pi And that leaves you guys with 0 to infinity, 1 over r squared plus s squared to the 3/2 power ds. This sounds like a job for you. I believe in all of you. So you wanna get crunching away on that? Remember how the electric field version of this was similarly challenging? It was a little bit easier because in the version of this for the electric field, it's based on the cosine of an angle. And so you had S here, which made U sub work okay. But for this one, we don't. So it's challenging. But remember how easy Gauss's law turned that problem into a pretty straightforward kind of symmetry kind of problem? There's something similar called Ampere's law that's going to do the same thing. And it's about magnetic fields and symmetrical systems of currents. So this will work. But I want you to be learned students. So there's another way you could go about doing this problem. I just want to make sure I still keep my stuff here. We don't have to do it in terms of ds. We could do it in terms of the angle. If you do it in terms of the angle, that does bring some trade-offs, but it allows you to get into using trig substitutions instead. So consider doing this in terms of the angle. We'd have to find a way to express r squared in terms of things that were constant and based on the angle. And we can. There's a couple ways to look at that picture and do so. So we did everything in terms of R and S. Let's do things in terms of big R and phi, okay? So I'm gonna erase all this because you already have it in your notes. And let's try. First, we need to find a way to express R squared in terms of R and this angle. So I would probably start by saying that we know that, just looking at my picture here, that, let's see, that what was I going to say? That, I lost myself. Sine of phi equals R over R. So R just equals R over sine phi. So R squared is going to be R squared over sine squared phi. This is going to allow us to do a substitution. And we already have a sine in there, so we're just subbing in. The next problem is, though, ds. We have to convert ds into something else. We can treat this as an arc length. Since we're dealing with trig, and we know that ds is really, really small, there's no reason why we couldn't write ds in terms of, say, r d phi. Now, it's not exactly r d phi, because that would be more about this angle and not that angle, but it should be close. Of course, that brings up another r, right? So we can start subbing into that. Bless you. But R now I'm going to do Now, one of these cancels with one of those, and then I can bring the sign up to the top, and I'll get sine squared phi over r d phi. This should give us the magnetic field if we integrate from pi over 2, 90 degrees, to 0. Right? Because phi is going to go from 90 degrees to 0. We will have to double it for both sides. Now, just keep in mind, sine squared phi is no picnic to do the integral for. But you have access to trig identities, which might make it something you could work out. Bit of a moment to have an aside to talk about permanent magnets. You guys have played with permanent magnets probably quite a bit over the course of your life. In fact, we've probably taken magnetic enclosures and magnetic fixtures to a pretty high level. I mean, how many of you guys have something that you have right now with you that connects some kind of magnetic in some kind of magnetic fashion? I mean, is it a keyboard that clicks into the bottom of your iPad? Is it my iPad pencil that clicks on the top? I mean, we love our magnets, don't we? We are just way into them now, and they're just awful convenient. Just a simple idea, and what must be probably the simplest current there is. And I know you're thinking current because I'm using that word, but I don't want that. What am I trying to do here? Border, fill, no. You already understand from chemistry that an electron isn't a point particle, that it's something else. We treat it like a point particle for a little while in chemistry, but then we understand that it's got some behaviors that aren't point particle-like. Maybe that wasn't your experience in chemistry, but I hope it's the experience of AP chemistry to talk a little bit about the odd nature of the electron. But even if we don't, the electron travels in what can be described as a circular path around the hydrogen atom. Now, it's not a perfectly circular path. There's way more to it, and if you study any quantum mechanics, you'll begin to understand that. But there is the idea that it's a current. If you take it back down to the idea of the Bohr molecule, there is a current around the outside of an atom. This current forms a current loop, and that current loop, by definition, would have a magnetic field. Now, we're doing a little bit of extrapolating, but taking the idea of the Bohr radius, you could start with a hydrogen atom and recognize that there must be a small magnetic field produced in every hydrogen atom. You would need to know how fast the electron travels around the atom, and it doesn't really travel like a point molecule. I'm reiterating this because I'm taking some excessive liberties with it. It has been found that there are a group of materials, mostly metals, that have a specific electron in a certain kind of shell, normally one of the S shells, especially S shells that are in the higher energy states, that allow for the production of a single current loop around the atom. If you look at this atomic structure of iron, iron has a high probability of being one of the materials that would have a small external current loop around each individual iron atom due to an upper level electron in that shell. That produces a single atom with a small magnetic field. Now, you know some things about magnets already. I take any two magnets in the room, get them close to each other, and what do? No, if I get them close to each other, won't they do more than just attract and repel? If I just place them on the desk, won't they attempt to align themselves? And if I bring them close together and they push apart, won't they flip themselves around to try and line up? If you can have an area where you have lots of molecules, and those molecules all tend to have a magnetic field passing through them. So I'm not going to care anymore about what the direction of the electron is, but let's just say that there's a magnetic field that passes through the center, maybe oriented in this way. Wouldn't be hard to imagine that if you had them a bunch, they may naturally pull themselves to be aligned. On the other hand, we also know that there is a general amount of energy that is inherent in individual atoms that tends to cause them to have their own motion. This would be attributed to temperature. And of course, that motion, that vibration, would cause them all to kind of be slightly misaligned. Now, if you could put them into some kind of structure where they were less able to move, say cool them down to a solid, it would lock their orientation in place. And if you did that, just say anywhere, say you did this on Mars, had an area on Mars that was very hot, and it was hot enough to melt the iron on Mars and then allow the Mars to cool on its own, the general motion of the particles would slowly place them in situations in which they would not have much alignment to each other at all. And you would not have magnetized iron. However, if you could liquefy the material and place it in a region of space where there was already a magnetic field. You see, I picked Mars because Mars has no magnetic field of its own. The only time it has a magnetic field is when it's near to Jupiter, and Jupiter's magnetic field impinges on it. But the Earth does have a strong magnetic field. So if you could get iron to be in liquid form, then most of these would start to align themselves. Unfortunately, I say align, but they would probably not be perfectly aligned for a number of reasons. The natural motion of the particles would prevent it, but also when you hit it with a magnetic field, it causes a torque, which then causes something to have gyroscopic motion. And we talked a little bit about that last year in mechanics, and if you're in mechanics now, we'll be talking about it in about a week and a half, the idea that you'll have precession. So they'll be kind of lined up, but not perfectly lined up. Now, if you allow this liquid to cool and lose its energy, it could harden and replicate the direction of that magnetic field. So any place in the Earth where liquid magma reaches atmosphere or reaches the ocean is going to cool and could cool in a likely situation in which the magnetic fields of the individual iron atoms line up. This produces permanent magnets. Now, we have discovered other materials, neodymium to be one of the more prevalent sources, where we could get a lot more strength of magnetic field per atom. And they're called rare earth elements or rare earth atoms. But this is how you make a simple permanent magnet. Now, it's not how you make a particularly strong magnet, but it's how you make a straightforward permanent magnet. But there's more description of this, and I would spend more time talking about it if I felt like it was going to be useful. Like the fact that most iron, by the time it has been brought to the surface, although it may have frozen with areas of it, patches of it, that have unified magnetic field, generally through natural earth erosion due to geologic activity. You know, the pieces falling down, breaking, reorienting, remelting, recoming together, being formed. You tend to get what are known as domains inside a material, all pointing in different directions. So if you want to make a magnet stronger, you could impose a magnetic field over liquid iron and then dry it under your conditions to force all the domains to be in the same direction. But I bring it up only to indicate something a little bit more, I think, interesting that you need to reckon with a bit. And that is, we still can't take away the idea that although there's a general magnetic field through the center. I'm saying this nicely. The truth is the magnetic field is circular. That's not what the magnetic field looks like. At the center of the loop, there's a magnetic field that points in a direction, but all of the magnetic fields that we're talking about here are actually circular magnetic fields that occur because of the nature of the motion of that charged particle that's passing around the loop. So the magnetic fields themselves are circular, and yes, as I get closer to the center, that magnetic field gets weaker, even though it's being reinforced by all of the other portions of the loop. The magnetic field is circular. The reason I'm saying that is because that means that even if you line up all those atoms, what you're really getting is a magnetic field that passes through the center, circles around the outside. Like that. So if the magnetic field is passing this way on the outside of your magnet, the magnetic field is passing this way. What do we call north or south then? Do you know? We based it on the Earth and the direction the lodestones moved, and so it was an arbitrary choice. But we called the point where the lines were going pointed in the direction of north. So that would mean that we would be calling this north and this south if this were a magnet based on the direction of the exterior lines, not the interior lines, because an object right here would see a magnetic field going this way. So the Earth, which we tend to believe, we tend to talk about its magnetic field, has a magnetic field that is generally believed to be generated due to the liquid center of the Earth. So if we look at the Earth as a magnetic field, as a magnet, it has a pole, we'll say, those lined up nice, pretty close. So it's spinning like that. The magnetic field currently are doing this, so they're pointing that way towards the top of the Earth, or what we consider to be the top based on where we stand. But that means the magnetic field lines through the Earth are going downwards. Now, the Earth's magnetic field is not well understood. We have ideas about what's causing it, but there are lots of unknowns. We know it has to do a little bit with the fact that the Earth has a liquid center, and the rate of the motion of the center of the Earth is different than the rate of the motion of the outside of the Earth. But there are other things that must be contributing to what's causing the magnetic field. We have geologic evidence that the magnetic field of the Earth is unstable. In fact, if you look at places in the ocean where we have ocean rifts and magma is coming up through those rifts, if you look and measure the magnetic field, you'll find bands of magnetic field there on the ocean floor, meaning that the magma comes up, comes to the sides, and while the Earth has a magnetic field in one direction, you create parts of your geologic surface that have magnetic fields facing that same direction. But we have them going in opposite directions, meaning there's a band that for a while faces one way, and then suddenly, in geologic timescales, there's a band going in the other direction. The only explanation for that is that eventually the Earth's magnetic field is going to flip directions and will be facing the opposite of this. Now, when that happens, the truth is, we don't really know how long that takes, because geologic timescales are pretty long, in the millions of years. We have record that this is occurring. More than that, we can measure it. It's actually happening fast enough now to see distinct differences in magnetic north versus true north. Enough so that we started to renumber airstrips. Whenever you see a landing strip someplace, it's got two numbers on it. The numbers represent the entry from one direction or the other direction, and they are 180 degrees apart. They're numbered in the hundreds and tens. There's no ones. So runway 12 is runway 120 degrees. You follow me so far? If you have to renumber a runway, you understand that that means it changed enough to change it to the 10th degree. Some of them had to be renumbered already. We know this is happening. We don't really know what it's going to do to the Earth or what will happen during the time that it's transitioning. We don't have enough geologic information about that. We know that the magnetic field around the Earth does have a purpose, or at least has begun to have a purpose for us, in that it insulates us from a lot of the highly radioactive and energetic solar wind particles that are streaming here from the sun. We talked about that a couple weeks ago when we talked about Aurora Borealis, but those particles are dangerous to the Earth. They can strip the Earth of its atmosphere, and more so, they can increase the natural background radiation for a time. Your sunburns become more extreme because you're being exposed to more frequencies of gamma and other particles that might have that effect on you. The Van Allen belts is an area of space that is filled with trapped charged particles from the solar wind. They're trapped in the magnetic field of the Earth. We do have some theories that part of the reason that Mars has such a thin atmosphere is because when it lost its magnetic field, and there's a reason to believe that Mars had a magnetic field, but when it lost its magnetic field, it was no longer as shielded from the solar wind as it was. Combined with the fact that Mars is a smaller planet, it had a harder time holding on to what it likely had as a very active and thick atmosphere like the Earth. But the solar wind's actions, plus not having as much gravity, allowed that wind to be blown away when Mars lost its magnetic field. Now, these are just, of course, theoreticals, right? We don't know, we weren't there. And it's us trying to do all the measurement from remote. We're not at Mars directly, we just happen to hang out there with machines a lot. But it's one of those things to pay attention to. This is why we monitor the sun so closely. We've already known that disruptions to the Van Allen belts can cause significant disruption to electronic activity on the Earth. In fact, so permanent magnets, this is how they're made, this is what they are. But it's important, again, for you to understand that if you have a simple permanent magnet, this is one of the things you probably should, with a north and south end. When you break the magnet, you don't isolate a north and south end. You create a new south end and a new north end. Because the magnetic field is circular. There are no magnetic monopoles. Should you find one, you will revolutionize physics. But currently, no magnetic monopoles. All right. Let's get back to the grind now. Here's something I want you to do, because you guys are learned people. We're going to take a few minutes and talk about the force between currents. So I have a current carrying wire with a current I passing through it, and we'll say that it stretches the length of the screen and is length L. It is currently generating a magnetic field. Could you, on your notes, put the X's and dots to indicate what side of this wire would have a magnetic field going into the board and what side of this wire would have a magnetic field going out of the board? That should be more than enough time. It should be that quick. So in this region, should I have X's or should I have O or should I have dots? Dots, that's right. There should be a field of dots here. That's definitely right. And we know that that field should be getting weaker the further away from the wire I get, because we know it falls off as 1 over R, right? That is the strength of the magnetic field due to the single current carrying wire. So mu naught I over 2 pi R. The further away I am from that wire, the weaker the magnetic field. On the other side, of course, I should have a field of X's, and they should have a similar structure because it's a circular magnetic field. So they get weaker the further away I get from the wire. So I bring another wire into the picture. And I place a current in it, I2 now, compared to I1. What happens to that wire? I know it produces a magnetic field, but won't that wire experience a force? It's a current in a region of space with a magnetic field. We know the size of that magnetic field. What would be the force on that wire? Come up with an expression. We will say it is a distance r away from the other wire. Come up with an expression for the force on the second wire from the first. This should take you just a moment because you know things and you can do algebra fast. All right, so is the force on this wire towards the first wire or away from it? Towards, that's right. They're experiencing a force towards the other wire. And since we know things like force equals IL cross B, and we know the size of B, it shouldn't have been hard for you to say force equals I2 L times this is all you have to do. This would be the force on this wire from the first. But of course, that wire also creates a magnetic field, which means this region of space has two contributions to the magnetic field. You should now work to figure out what force is acting on I1. Furthermore, tomorrow we're going to flip the wires because it seems like currents tend to attract each other together. You should see what happens to unlike currents or anti-parallel currents.